Today on Hands-On Maths, we're looking at the Fibonacci sequence. We're going to do it with blocks, and that's going to give us some insights into the sequence. The way I'd like you to do this is to download the worksheet from my website, which is free. It's a 2-page worksheet. It can be printed back to back in black and white. And also, you'll need some 2-centimetre cubes. These are available online, or maybe you can get them at your local teacher's shop. Let's talk about Fibonacci himself. He was from the West and the East, and zeroing in on the Mediterranean, he was born in Pisa, Italy, in the region of Tuscany. But he was educated in Bugia, which was in the Almohad Caliphate of the day, and its modern-day Beja in Algeria. This came about because he was the son of a customs official and merchant who did a lot of business in North Africa. Fibonacci grew up knowing both Arabic and Latin, and he was taught mathematics in Arabic. His most famous book is Liberabaci, published in 1202. Now, Liberabaci means the book of calculation, and this was really about how to make calculations in business in an easier way. And he introduced the Hindu Arabic numerals, which of course have the advantage of place value. In Europe at the time, everyone used Roman numerals, which were very cumbersome. Also in Liberabaci was Fibonacci's famous rabbit problem. I'm reading from the worksheet. A pair of baby rabbits takes 1 month to mature. A month after maturing, they produce a new pair, and every month after that. The baby rabbits follow the same process, as do the pairs they produce. How many pairs of rabbits will there be after 12 months, assuming that none die? We're going to do this with blocks, and we're going to make baby rabbits red, mature rabbits yellow, and reproducing rabbits green. And the fascinating thing about this is there's only 3 sorts of blocks. So let's get started with a red block, and this will be generation 1, followed by a yellow block, which is a mature pair, followed by a green block, which is a reproducing pair, and ever after that, that generation is reproducing. Green, green, green. A month after a pair of rabbits matures, they produce a new pair. So that's the second generation, red, yellow, and then green, green. Every year, a reproducing pair produces a new pair. So that means that the first generation will again produce a pair of baby rabbits, which will become a mature pair, which will be a reproducing pair. In the following month, both the first generation and the second generation will produce new baby pairs, which will be red and yellow, and red and yellow. Now, a month after that, you can see the first generation, the second generation, and the third generation will all produce a new baby pair. Now we have to look for a pattern in this growth, and we see that 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, 3 plus 5 is 8, and then 5 plus 8 is 13, and 8 plus 13 is 21, 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89. And 55 plus 89 is 144. And that is the answer to Fibonacci's question. 144. And we see it's following this formula, that the nth Fibonacci term is the sum of the two terms before it. Can we explain this formula simply? Yes. The row before row n is n minus 1. Now, no rabbits die, so all these rabbits keep going. So where do our new baby rabbits come from in row n? Well, they come from the rabbits that were in n minus 2 row. As you see, in row 6, there are 3 new pairs of baby rabbits, and there, in row 4, there are 3. So that explains the sequence. Now there's something very interesting going on here. We've set this up with 3 different sorts of blocks. Red for baby rabbits, yellow for mature rabbits, and green for reproducing rabbits. Let's count the population of each of those. Well, remember, red rabbits are really our growth. And since the whole population is growing in a Fibonacci way, then that growth will have to also be Fibonacci. But let's check on our model. And we see it goes 1, 0, 1, 1, 2, 3. Now the following row will be n minus 2. It will have 5 new pairs of baby rabbits. So let's fill out that row. Now we move to yellow blocks. Well, yellow blocks, the mature pairs, will be following the baby pairs exactly, just 1 month behind. On our model we see it's 0, 1, 0, 1, 1, 2, and of course we see that we have in row 6 3 new baby pairs, and they will become 3 new mature pairs, and that will be 3, because the existing mature pairs will become reproducing pairs. So let's fill out the table for yellow blocks in the same manner. And now we come to green blocks. Well, green blocks begin by following the red pattern, but then they repeat infinitely. Our overall growth pattern is Fibonacci. From the model, the green ones look like this: 0, 0, 1, 1, 2, 3. And the next row will be those 3, plus there are 2 yellow blocks, they will become green. So that'll be 5. And now we finish off that column according to the Fibonacci sequence. Now we'll check to see if each of our rows add up to the grand total on the right, which is our overall total. And we see that indeed it does. What's interesting about this is that within a system growing at a Fibonacci rate, there are populations within that system also growing at a Fibonacci rate. Now we go over to page 2 of the worksheet, and let's look at the first task, which is to do a Fibonacci spiral. The right way to do this is to use a compass and to do an arc, which would be a quarter of a circle, within each square. But since the first 2 squares are 1, 1, we can continue with the same arc but the square below that is going to be 2 by 2. So the arc will look like this. The next is 3 by 3. So the arc will look like this. The next arc is 5 by 5. And that will look like this. Now, unfortunately, I don't have a compass at hand which has a wide enough radius to do the 8 by 8. It's going to turn out just like the one in the diagram. Now, the next task is to build a shape which follows the spiral with blocks. So that starts 1, 1, and then 2 by 2, which is 4, and then 3 by 3. These are the squares of the Fibonacci numbers. So the next one will be 5 by 5. And the next one would be, of course, 8 by 8, if I had enough blocks. Now there's an interesting thing to note here. That is, if we add the squares of 2 consecutive Fibonacci numbers, we get another Fibonacci number. So in this case, 4 plus 9 equals 13, another Fibonacci number. 9 plus 25 is 34, another Fibonacci number. 25 plus 64 is 89, which is another Fibonacci number. Let's have a look to find if there is a formula for this. And I'll go through the examples that I've just done to try and find that formula. First, I'll write out the Fibonacci sequence term by term, just to know where I am with each of them. So, of course, that's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and 233. Well, I said before that 4 plus 9 equals 13, so that would be t3 squared plus t4 squared, and that would equal t7. So let's try another one. 9 plus 25 equals 34. Well, that would be t4 squared plus t5 squared equals t9. And one more. 25 plus 64 equals 89. So that would be t5 squared plus t6 squared equaling t11. So what's the rule? Well, you can play around with it, but you'll find it's t to the n squared plus t to the n plus 1 squared equals t to the 2n plus 1. Okay, the next part, we note that dividing each Fibonacci number by the previous Fibonacci number gets us closer and closer to the irrational number phi, the golden ratio. And now we get to the final question on the worksheet. The task is at the bottom. It says, using the above formula, can you find how many rabbits there will be after 5 years? This is using Binet's formula. Binet was a French mathematician. And if we look at the formula, we see it's simply phi to the n minus the conjugate of phi to the n, all over root 5. Now the value of the conjugate of phi is negative 0.618, and so on. So when the power is even, this is a positive number, and when the power is odd, it's a negative number. And that's why you get this oscillating value that you see in orange on the left, whereas the yellow is just the value of phi to the n. When the powers get very high, over 50, this value of the conjugate becomes negligible and is less than 1/1,000,000th. I'll now do the problem using Binet's formula. The question is, using the above formula, can you find how many rabbits there will be after 5 years? In other words, when n equals 60. So that will be F60. Now, it's phi to the 60th power minus the conjugate of phi to the 60th power. All over root 5. Now, this is the conjugate of phi, it's not the reciprocal, and the conjugate is sometimes represented by phi with a hat on it, or phi prime. I've used phi bar. Now, as I mentioned previously, the conjugate of phi to the 60th power has a value of less than 1/1,000,000th, so we can ignore it. So we just have to calculate phi to the 60th power over root 5. Now you can put phi as a constant into your calculator to help you calculate this, but when you do that, you'll find the answer is 1,448,008,755,920 pairs of rabbits there would be after 5 years, following Fibonacci's rules. The 60th Fibonacci number. Okay, that's all for this video. You'll find more videos on hands-on maths on my YouTube channel and on my website, mathswithgeoboards.com. Thank you for watching.